Welcome everybody on Zoom. Welcome everybody in the lecture hall to this new lecture of the Big Data course. So what's on the menu today? First, I'm going to finish and wrap up on white column stores. I'm going to take the time we need in order to make sure to answer all of your questions and go again into some of the details that might have been tougher. It was a tough lecture, right? It's one of the toughest ones of the course, so we can time needed. And when we are done with white column stores, we'll move back to data modeling of denormalized data, and in particular, how we validate schemas. And in the end, we'll arrive to the popular data frames that you probably, who heard about data frames? Plenty of you, right? So we'll arrive at data frames at the end. Okay. We start, I will ask you a question on white column stores, then I'll take questions, and then I'll continue. So you remember that at the physical level, we have key values. This is the way that cells are stored in HBase, right? So where are they stored? On the disk, in a write-ahead log, in memory, memory for fast retrieval and the CPU L2 cache, just on a write-ahead log and memory for fast retrieval. So what do you think? Is it all under control, the waiting room? I see that there are people. Do you see them in the waiting room? Oh, this is why. Yeah, I just wanted to make sure if everything was okay, because there can be technical issues. So let me see. So I cannot see you anymore. Oh, here you go. Yeah, perfect. I thought that something must have happened. Okay, let me also admit them. Yeah, thank you. All right. So let's take a look at your answers. And there is a majority. Is the majority correct? Yes, it is. So indeed, it's at plenty of places. So it's on a write-ahead log. The write-ahead log is just in case we have a problem that there is a crash and we lose everything that is in memory, it's gone forever. If we put it in a write-ahead log, then we make sure that we can recover it if something happens to the machine before we get a chance to flush the data in memory. And what's nice with the write-ahead log is that you're just appending and appending and appending, and this is no problem on HDFS. You can append to files all you want. It's part of the API, right? So this is why we have a write-ahead log. But the write-ahead log is going to record the data in order of change, right? It's really timed based on the order in which you make the changes, as opposed to the H files in which it's sorted by key. All right, so first the write-ahead log. Then we have the memory, what we call the mem store. We saw last time, one of you actually asked the question, it was a very good question, and I looked into it, that indeed the mem store is actually implemented in memory with a concurrent skip list map, right? So what does it mean? Concurrent means that it's thread safe, so you can access it via several threads concurrently. And the idea of a skip list is that it's basically something that makes searching faster. Imagine that you have a linked list that goes through all of your key values, and then you build another linked list on top that builds on that links some of the key values, a subset of them. Like, for example, every second one or every fourth one, for example, but you pick them randomly. So it's like taking a shortcut, but you skip a few of them every time. Then you add the third linked list that maybe has every 10th key value, then another one that have every 100th, right? And all the way to a very sparse linked list at the top. And the way you look up key values with a skip list in that way is you start with the top one. So that's literally a highway that directly brings you that skips an enormous number of key values. And you just look up your key value by comparing on the key values you see at the top. It's very sparse. And as soon as you find that you are greater than a key value, then you know you're in between the two key values in your highway linked list. Then you go down one level and try again with that interval, find where you are and go down and down and down. So you basically get to the more and more specific linked lists every time until you find your key value in the end. For whom does that make sense? Right? You can look it up. It's called the skip list. Okay. And the one at the end, map, is just that you organize the keys as a skip list, but then you map at all the leaves, all the key values that are in the bottom skip list. Then you associate the values, of course, that go with the keys. All right. So this was a question that was pending. There were actually a couple more questions that you asked. I don't know if you saw in the Moodle, if you go to the Moodle of the course, in the I think it's called Moodle Overflow as a hint to Stack Overflow, I added a few follow-ups, so you can take a look at them. I can also mention them in the lectures, but this is where I typically put my offline investigations whenever I don't know an answer, and I investigate more offline, right? So don't hesitate to ask questions. I don't know everything, but if I don't, I just try to figure it out. Okay, let me now go back. Yes, I will make you host again. Let me share the screen. This one, then I'll you enter immediately. Oh yes, I see what happened last time. I just let you in, but I didn't make you co-host again. Now you are here with a co-host. All right, thank you. Okay, so just to recap, in a white column store, the high-level model is that we have plenty of rows that are identified with a row ID, sorted order, the row IDs, it's in ascending order, and then the columns are organized in column families, right? And within the column families, there are columns. The columns can be created on the fly without any performance impact. But if you want to add new column families, that has a bit more of a performance impact, so you don't want to do that too often. Then we saw that it's like this birthday cake or wedding cake that you cut like this horizontally and vertically. And every intersection of a region, which is just a row ID interval and a column family, gives you what is called a store. And everything that is within one of these slices here is what we store together. So for every one of these rectangles, every one of these stores here, for example, this one right here, you have one mem store, meaning a concurrent skip list map in memory, and you have all the H files that correspond to older data that were buried in H files. So we saw that the logical map, on the logical level, you have cells in a table, but on the physical level, we list the cells physically as just a list of key value pairs ordered by key. And we saw that the key has the row ID, the column family, the column qualifier, and the version. I also had a question on version. So I actually looked it up a little bit and educated myself digging request. So if you insert a value, it's just going to use the current time as the timestamp. If you're not happy with that, you can specify a different timestamp. That's also allowed. The API allows you to override the timestamp and do something else. And then the next thing that you can do, of course, if you create new values and edit values, we saw that it doesn't really delete them, it just adds a new version, right? But if you keep updating the same value over and over and over again, at some point, that's going to be a lot of versions, right? So what happens is that you can specify for every column the maximum number of versions that you want to keep. And what's going to happen is that if you say, for example, I don't want more than 3 versions to be kept, then periodically it's just going to get rid of anything beyond 3 versions. It's going to keep the latest 3 versions and just get rid of the others. Now, my question to you to see in terms of thinking, when do you think we can get rid of all these versions that, like if there's more than 3 versions, what is the opportunity when we can get rid of them? Yes, maybe the catch box. Oh, it's there. Did it work with the batteries? Let me see if I manage to. Where are you? Oh, there. almost. Yeah. Let's see if the volume needs to be adjusted. There you go. Doesn't work. Is it switched on? Yeah. So basically, but if I just said, you basically said when we write the files or when we compact, right? Exactly when we compact. And this is the correct answer. Because what we saw is that in HDFS, you cannot just go ahead and edit a file anywhere you want. You cannot have random access updates in the files. The only thing you're allowed to do. Okay. Oh, great. That's sorry. So the only thing you're allowed to do on HDFS is to create new files or to append to an existing file. That's the only thing you're allowed to do. So when can you actually modify data? Only when you flush and when you compact. These are the only two occasions. So as long as you don't flush or don't compact, you just accumulate new versions without getting rid of the old ones. And as soon as you compact, this is the moment where you can say, okay, let's do a bit of cleaning up and throw away all the past versions that we don't need. If we marked some of the values as deleted, because also when we delete things, we don't actually delete them. We just add some what's called the tombstone marker to say, okay, this must be deleted. And when you compact, you can notice, okay, now this value was deleted. Let's just throw everything away. And in the new compacted H. Okay, so as an explanation for the people on Zoom, the network just cut. Because the network cable that's supposed to connect us over LAN was actually not plugged. So, but now we can continue. What's the last time that you heard on Zoom when I was speaking? The last thing you heard? Okay, I see on the chat. Compact and flush, yes, exactly. Okay, so let me now take it from there. All right, so I was saying that whenever you compact or flush, this is your opportunity to get rid of the key values you don't want anymore. This is your opportunity. And I was saying in a newer version of HBase, they introduced also the ability to compact, meaning to get rid of those values directly in the memory before you even flush. So that actually can reduce the amount of data in memory if you write a lot. And then we had a question over there, and this is, I think, where we left. So who had a question? They're over there, so we can throw the catch box. Yeah, awesome.
Is the amount of concurrent versions per column family or per column?
So the version of the mem store, you mean, or the skip list?
The amount.
Oh, the number of versions, you mean?
Yes,
the top
versions.
I think, as I understood it, it was per column. When I understood it. I can double check if you want, because it did sound strange that it wasn't column family, but I think when I read it, it was column.
Because we store them in memory, like all column families, right?
Yep.
So that would be a little weird.
Yes, it is indeed something strange. This is also something I can investigate even more. So the idea is simply that, you know, when you look at the mem store, it's just this list of key value pairs, right? Just a list of key value pairs. So what you do is that when you actually do the flushing on where you check in order to compact, you kind of group the key value pairs that have the same row and column qualifier and column family, which is easy because it's sorted, right? So the grouping is trivial, and then you just throw away what is on top of that. I will double check again that it was column and not column family, because this is actually a good question, right? Because if you want to specify it on every column, you don't know them in advance, right? So this is, I can totally understand your question, right? So let's take a note of that for later, that I will also investigate. Thank you. There's good thinking. It's nice that you think in that way. Okay, so I have the few recap slides. So I was saying that, yes, you have the different versions of the same cell. I actually noticed that, I don't know if they've always been doing that, but apparently they store the versions in reverse order. So they start with the latest versions in order to find them first. So this is actually the descending order when they do it in HBase right now. Okay, so we saw we have the mem store with this concurrent skip list map with all the recent values. And the more you go down, the more you have the older and older and older key values that were basically buried into H files like there. And so if you look at the whole hierarchy, this is just if I turn that by a right angle, so this is what I get. So you have the C0, which is basically the mem store. This is all the fresh data that is in memory, right? And then you flush to a first level of H files on the disk, right? This is your first level called the C1. And then what you do is that when you have too many of them, you compact them to bigger H files. And what actually happens is that you keep burying and burying and burying the key value. It's like archaeology, right? So this is all the fresh stuff. This is the things that are still recent. And the more you go, the more it's archaeology. I don't know if you find dinosaur fossils if you go to the really deep levels, but this is the idea, right? You keep burying and burying the older the data gets. All right, for whom is that clear? Okay, we have a question over there. And just throw it, yes.
One thing I'm not sure I get is the skip lists are built from the contents of the H files, right? And they are kept in the mem store. But then in the mem store, we are going to have values that we haven't written yet to the H file yet because we didn't have a flush yet. So then yeah, my question is related to how adding new entries that sort of fit in a specific skip list, how are the updates there done, or how it's gonna know that, you know, it pertains to. I don't see the correlation of new values and existing values in terms of the skip list.
Just to be clear, what is in the memory does not come from an H file. Right, it's what has not been written yet to an H file. So this is all the fresh things. So if you look at the data flow, there's the user inserting something, it's flushed to the write ahead log, and then it's put in the concurrent skip list map, right, in there. How the skip list works and so on, it's out of scope of the lecture. There's a whole bunch of algorithms that tell you how you insert a new value in a skip list. You basically insert it to the bottom linked list, and then you throw a die every time to see if you also add it to the upper highways, linked list highways. That's the idea. But basically, this is just what is in memory. It's all fresh. And then when you flush it, you go down the bottom linked list of the skip list and you flush everything to the H file, removing any extra deleted values if you want. Does it make any sense, or do you still have a question? Yeah, awesome, perfect. Don't hesitate to ask questions, right? It's also good to keep repeating. All right, so we have now established this whole idea of flushing and compacting. I told you I took the example of base 2 for the idea of flushing and compacting, meaning that every time you have more than one file of a given size, you compact and create a larger file, and it actually comes down to counting in base 2, right? It's like when you do 1 + 1, you write a 0 and then move on to the next digit, and then you get 1 0, right? So who sees that it's counting in base 2, this whole flushing compacting? Okay, awesome. Who sees it can be generalized to any basis? You can also do it in base 3, in base 4. Okay, all of you, perfect. So that was pedagogical base 2, right? But in reality, you can have a higher basis. All right, awesome. Okay, then, and this is maybe where the confusion came from earlier, you can still keep some of the data that is actually buried in H files. You can keep a copy in memory, but it's not the mem store, then it's something different. It's a cache, right? This is explicitly a copy of something that is in the H files. There are cases where the caching doesn't work at all. For example, if you just batch process, which we will see with MapReduce and Spark, then you just scan the entire data. There is no point in caching anything in that case, right? Just go through the entire data anyway. And the second case where you don't need to use the cache is if you keep accessing randomly all over the place, and then you never get twice to the same value. So here the cache is not of much use, right? So these are the two cases. But on the contrary, if you keep accessing the same data, it's called hotspots, then you can actually use a cache. All right, that's the first optimization, the cache. There is a second one, optimization. Let's go through this. What if you have a lot of H files? Even with, let's say, base 10, then you have plenty of H files to read from on disk. And I told you, if you want to read values for a query in HBase, you need to look everywhere, in the mem store, in the first level H files, in the second level H files, even in the dinosaur H files, you also need to read everywhere. Can you improve that? Yes, and that actually is one of the biggest ideas in big data, in many other technologies. You actually can organize things in such a way that you don't actually need to look at all the files. You can actually, for each file, very quickly see if you actually need to look into it. And one of the ways is that in each H file, you can store at the very beginning in a way that is super easy to access the minimum and the maximum key. For example, right here, in every H file, you quickly see the minimum and maximum key. Imagine that here, the key you're looking for to execute your query is higher than the maximum key in that H file. Do you need to access it? No, you can just keep it because you know that all the keys in there are anyway lower than the key you're looking for. So you know this, there is no way you're going to find the key here. So you can actually select just the H files that you know the key might, you're not sure, right? It might be in there, but you can exclude the H files for which you know for sure that it certainly is not going to be there. For whom does that make sense? This is a super important principle of big data. It's used as plenty of other places in query optimization, on data lake to read data. You can add some metadata on the files that give you the intervals or meta information on the data. And with that, you can just skip reading an entire file completely. And when you know that very often the bottleneck of your big data system is reading files from disk, then if you can just keep reading an entire file, this is a big performance improvement. So this is super important. Now, this works in the case that you have these intervals of keys, and then you're lucky because it's higher than the max or lower than the mean. But what in general, if you look for a specific key value, but that might actually be in the middle of an interval, right? So you might still have too many H files. When there is a magic solution, that's called the Bloom filter. The Bloom filter is a magic construct. Well, it's a magic if for the people, you know, any sufficiently advanced technology looks like magic, right? So it feels magic. The Bloom filter is a black box or a data structure that tells you with certainty that a value is not contained in a specific file or in a list, or that maybe the value is contained in it. So there are two possible answers coming from this black box when you ask the question. The first answer possible is no. The second possible answer is maybe. Yes, you will never get. You will never know for sure if a key value is in there. You will have a no and you will have a maybe. And this whole structure is based on hash tables, on the use of plenty of hashes that you use in order to populate a bitmap with zeros and ones, right? And then you mark, and then magically it's going to give you an algorithm that does that. It might be the TA team will show that to you in the exercises a bit deeper, the Bloom filter, if my memory is correct. For the purpose of the lecture, I'm not showing you more than that. I'm just telling it to you that it's a data structure, it's a physical structure that is very good at telling you for sure that a key value is not going to be in an H file, or maybe that it's going to be in it without being sure. And that way you can eliminate plenty of H files when you know for sure that it's not in there. And you can imagine the gain in performance that you get by not having to read the H files. Okay, now something new. How do you bootstrap the whole thing? How do you know where to actually look? How do you know which region server to contact if you're looking for specific key values? Well, there is a meta table somewhere. There is a meta table that stores the information of all the column families and regions over the entire HBase system, right? It's actually sufficiently small that it actually fits on a machine. So typically it's going to be stored in one of the machines that everybody knows where it is, and then you can go ahead and go there. The exact way that it works on the physical level also involves a technology called Zookeeper, but that's not part of the scope of the lecture, right? So all you need to know is there is a meta table somewhere that knows what the regions are and which region servers are responsible for what, then you know how to connect. So if the client wants to create, delete, update a table or whatever, or query, they ask for the so create, delete, update goes to the HMaster. They query the region, they get the region server locations from the meta table, and then they can connect to the region servers in order to get the key values, right? Of course, who does that? It's not the end user of HBase, it's more like the driver of HBase, right? Because the end user sitting in front of the shell doesn't need to actually deal with this, right? So this is just a low-level thing that is happening when you type things on your HBase shell, all right? So what's important here is you have this meta table that knows where the regions are located and assigned to the region servers. You have a REST API for HBase, and you also have a Java API because a lot of things are implemented in Java, or we will see later also Scala for the case of Apache Spark. So you have the choice between communicating with the REST API or using an API in Java. Or you have the shell, but basically the shell is probably connecting via either of those. Okay, I wanted to share a few thoughts, also high level, on how this connects with HDFS. Because you might remember I told you about short circuiting. I told you that the region servers are often able to short circuit HDFS, and they can directly read the blocks of the H files from the local disk where they are sitting, right? Remember that the region servers are processes running on the same machines as the data node processes, and that the blocks in HDFS are actually physically stored on the local drive of where the data nodes are, right? So what happens? Imagine that you have just flushed or compacted or whatever the data. We saw that H file is an HDFS file. So the region server is a client of HDFS. It's going to use the HDFS protocol to write down the H file. And where do we store the first replica of every block in HDFS by default? Yes?
On the client's node.
On the client. And who is the client?
In this case, the region server.
It's the region server. So what does it mean that it's on the machine where the client is? Well, it means it's on the machine where the region server is writing the H file. So it means that if we look at one of these machines here, where there is a data node and a region server process, when the region server flushes an H file, it will put the first replica of every one of the blocks of that H files right here on the same machine on the local disk. Of course, there will be other replicas that are going to go over the network to other machines, right? But we have them all here. So you can now understand that if you want to read it back, you don't even need to go over the network of HDFS. You can just directly read it as a local read. That is much faster than reading over the network. You don't even need to go to the name node, right? So this is what we call short circuiting. Yes?
So I have a question that's sort of related to searching a specific key. So thinking about HDFS and knowing that there, the name node knows about the locations of each of the files, and therefore it can tell us quickly enough where we can find it and where we can fetch it. I was thinking what would be the sort of trade-off in terms of performance and cost to maybe in case of HBase, where keys are already sorted in the H files, what if we could have maybe a node that stores all the keys and where they can be found, and we just do like a binary search there or try to do something in logarithmic time so that we don't use something like Bloom filters or
This is very clever. It's very good thinking. I think I mean, what you're saying makes sense to me. That's something that you could try. Of course, then what you would need to look into is basically make more calculations about the total size that it would be, right? If you store the keys without the values and so on. But it's probably the sort of thinking that you would have in the engineering team, right? When you design these things. I mean, it needs a bit more thinking and digging, but on the high level, it's not a bad idea at all to try these sort of things. There is another comment here.
So I also thought about what he just said, and to me, it seems that the binary search will bring more problems, because to do the binary search, you have to actually compare the value. So you have to bring it from disk into memory, which is still slower than just looking at the Bloom filter. So I think that was the reason that I came up with why we would not want to do that.
Yeah, that's good thinking too. You know, this is probably the discussion you would have, you know, if you would join the engineering team and think about these things. This is probably the sort of discussions you would have. So that's very good thinking. You would probably, if I think from the top of my mind, you would probably just store the keys, right? So the values you could probably drop. So it comes down to how much space do the keys actually need. this idea, it's basically the sort of discussions you very often have when you have an index, because this is an index, right, that you want to build. So whenever you have an index, we'll study them in a few weeks for document stores. One of the important questions that you have is, does my index fit in memory? In many cases, the entire index fits in memory. Then accessing the index is super fast. In some cases, the index doesn't fit in memory either because it's too big or because there are too many other indices on the same machine, right? And then you have to design the index in such a way that even if it doesn't fit in memory, then you basically have the upper part of the tree. So when you say binary search, you can mean a tree structure or a skip list or whatever. So you keep the upper part in memory and the bottom part stored on disk. And then you only access the bottom part that you need to actually access, right? But this is fundamental thinking. I mean, it's exactly the sort of things that you consider when designing these sort of things. So we have maybe you, and then we can go to you after that.
Yeah,
Right.
so I read the H-based paper and about this specific part about storing about how you can short circuit the H file and the H block. So it mentioned that initially when you do store it, you store it on the same client, but then it might happen that rebalancing happens over some additional. Yeah.
Is it what you mean? Yeah, it's great. So this is exactly the idea, right? Do you want to continue to finish your thinking?
Yeah, so I didn't agree with I didn't understand fully what was said in the paper because they said that even though the block itself is moved during a rebalancing operation, they said that compactions happen often, and during compaction, the block is again written on the same machine. But I'm not convinced because the larger blocks, so we're counting in powers of 2, right? So then we will very quickly end up with some very, very large H file or H block. And that very large one doesn't get compacted as often. So if it does move to a different node, how are we so sure that we will indeed be able to find it on the local machine? And because it is so big, it contains a lot of values. And I think that sort of like similar to cache misses may happen often, and I think that's an issue, and I wasn't convinced by the paper.
I think it makes a lot of sense. So the argument, I totally agree with the argument, right? So basically, if you don't go all the way to the dinosaur fossils, but you stay on the higher level of burying, then you probably still compact often enough that this basically happens. So whenever you compact, the new blocks of the H file get back on the same machine. This happens when you let the system evolve, right? It just can, the blocks can then end up somewhere else. But then when you compact, it goes back there. But of course, you make a totally valid point that for the very, very, very old H files, the bigger ones, you don't compact that often, and then you run into the issues that the block starts to be, at other places. So you could, of course, then, change the design a bit. For example, you can periodically rewrite these H files, or that sort of thing. So you can always remedy to that. I don't know if this is something that actually that they addressed. It's a very good point. Either there are several reasons possibly why it wasn't addressed. It might be that practically no system actually reached a size at which you start having these kind of problems. Probably because you remember that we split the regions, so you can control the parameter to split your regions. And when you split the region, at some point it becomes so big that then you create new files all over again. So maybe splitting the regions is the solution to this concern.
Makes sense.
I'm thinking on live here. So, but it makes a lot of sense. This is very good thinking. Yeah. So I think you were next, and then over there.
Why don't we store the metadata table in HMaster? Because this way we have to do we add network latency.
That's also a good question. It might be to not overload the HMaster, because it's the same thinking as when we had the job tracker in MapReduce, to not put everything at the same location. That's how I would imagine that would be the reason. That there used to be, as far as I can remember, in HBase, multiple levels of metatables. There was a metatable, and then there was a second level of metatables that were distributed. And at some point, I think they dropped the second level and just have it at a single place. The only reason that comes to mind, this is also something I can investigate more, but it would be to not overload the HMaster. that you want to do it somewhere else. Does it make sense?
Yeah, thank you.
All right, over there.
So for David's question, at least like half of the files are always stored in the largest block, right? In the compaction process. So it's not just the fossils. So it's probably the redistributing.
Yes.
Thing that
So
you
when,
said,
when I
right?
use the word fossil, it's only a pedagogical thing, right? It's just to convey the idea that you bury stuff. But in fact, yes, if you consider in terms of importance, it is indeed in the case of base 2 half of the data that is sitting there, right? That's a very good point. In fact, even today, if you count the total number of human beings that have ever been on the planet, so today they are, I think just in a month, there will be 8 billion, mid-November. But if you consider the total number, I saw several estimates. I think the smaller one that I saw was 50 billion human beings have ever lived on the planet, and maybe all the way to some people saying 100 billion or something. But that basically means that every 10th human being is alive today for the entire history of mankind. And then you would argue, okay, 99% of the people who ever existed are no longer with us. So it's the same kind of thinking. But yes, so what I mean here is it's an analogy, you know, to pedagogically explain the idea of burying. But like every analogy, there's always a limit to it, right? Okay. Any other comments? All right. So in order to finish, because now I'm done, so I'm happy you had all these questions. So we discussed this in more details. Now I want to show you some of the newest things that there are out there that happened even later that takes it to the next level. This is a newer design called Spanner. It was done at Google. That is even larger. And you see that there are several things that happen here. So first, you notice there's multiple columns for the primary key, not just one. I think Cassandra is doing the same. So you have multiple columns here. But another change is that you don't have just regions, you have the tablets that can actually be unions of intervals. So there is a bit of a relaxation right there. The timestamp is put in an additional column over there. But what's really, really new is that here there are so many zeros that I have to think when I read it. So it's a trillion. So you can have trillions of rows in the system. So now you're going to tell me, how do you fit trillions of rows in a data center? Well, you don't. You actually need plenty of data centers for that. And this is when it actually starts feeling really great to do. I mean, I imagine the fun that the engineers must have had there. But basically, you have all of the H masters, or what would we call an H master in HBase, and then you have the universe master, like a central node that basically looks over all of the data centers. So here you really have to imagine plenty of data centers all over the planet that you don't only shard across machines, but you even shard over data centers, right? So we are talking, well, a company has hundreds of them, right? When you're Google or Amazon or Azure, you have plenty of them, right? So we are talking about millions of machines. So you see the scale is totally different, but there is a way to even make it scale even more than just on a single data center, right? So this is actually new because everything we had done until now was still fitting in a single data center, right? But this is the sort of things that are happening now. All right, this actually finishes the lecture on the white column stores. I see it's 2:56. I think that given how well you participated and all the questions you asked, you deserve the break, so I can give you a few minutes. And we will start again at 3:15 and start with data modeling and data frames and validation and all of that. So thank you very much and see you at 3:15 for the continuation.